guys, in this video I'm gonna show you something about the properties of uniform convergence sequence. So last video I introduced you the concepts of uniform and pointwise conversion, right? And I said that uniform convergence sequence actually have a lot of interesting and beautiful properties. So actually in last video we've introduced one of them, which is about the continuity. So when we look into the properties of uniform convergence sequence, we mainly look at the limit function, the function that is being uniform converged to, right? The function f. So in the last video I've already shown you the theorem about the continuity, right? So let's go back and see it. The theorem says, given a sequence of functions and if f and r continuous, all the functions in that sequence is continuous, and f and converge uniformly to the limit function f, then the limit function f must be also continuous. We said it can be used to check the uniform convergence, right? If the limit function is not continuous, but the sequence of functions are all continuous, then the convergence cannot be uniform, right? And another thing I didn't mention is that we can actually have this result saying that limit x to when we take the limit x to some point c, and we are trying to look at the limit of the sequence of the functions. But what is the limit of the sequence of functions? First of all, the limit of the sequence of the function is a function, right? Because you want to know the value of a limit when x approaching some point, then you must first of all get a function, not a sequence of function, right? As a sequence of function, at one point it might have different values, but that value under the if the convergence is uniform, that value can be that different values can tend to some value, which is the convergence like point or value, right? So first of all, inside the double limit, the limit of the sequence. Oh, I didn't know if I covered it. Okay, so the limit of the function, the limit of sequence is first of all fx. Then you take the limit when x is approaching some point c. Then you get fc, right? But actually you can interchange. Interchange the interchange two limits. So you can so when I say interchange the limit, from this example you might not see what what happened, right? But the thing is, if you ask to give the limit of a sequence of function at some point, you don't go directly to the sequence of functions, but you first find out the limit function that the sequences are converging to. Then you try to get the limit of that limit function when x approaching some point. Okay, so I think this is the meaning of the property, the continuous property. Okay, so let me just show you the proof of the theorem. So the proof is actually quite straightforward. It uses the classic triangle inequality. So we want to show that f is continuous. To show f is continuous is quite straightforward. To think of how we're gonna show it's continuous, to use its like definition, right? So to show f is continuous at some point, say at point C. So we want to show f is continuous at like x equals to C. So that is actually we want to show that fx minus fc. So say the functions here are all one dimension, are all from R to R. Okay. To simplify the proof, we just show. I'll just show you that, or like we make the assumption that these functions are from R to R. It's actually similar if you if the functions are from like R3, R4, Rn to R. It's quite simple. So suppose the functions are from R to R, then we want to show this is R to R and D1. Sorry, I should mention the distance function is D1. Okay, so fx minus fc, take the absolute value of it would be, you want to show it's small. It is smaller than epsilon, right? But if we go directly to the difference, we want to get anything, right? Because the only thing we know is that f is a limit function, but we want to have some connection to the sequence of function, right? Because the sequence of functions are uniformly converging to the limit function f, and a more important thing is that they are all continuous. We have to use the their continuity to like show the continuity of the limit function. So what we have, the conditions that we have is that fn is uniformly converging to f. So that gives us fn minus fnx minus fnc is going to be smaller than like epsilon, or you can take like half of epsilon or something. It doesn't matter. It's just a number, just a positive number for all n larger than n, capital N, right? So okay, this is the first thing we have, and the second thing is that the continuity of fn. So what we have is since fn, all functions fn are continuous. So when we are taking the continuity of the functions at the point C, we have fnx minus fnc is smaller than like epsilon. We just take it for epsilon. If we need some change, we'll change it backwards. So okay, then so I did write down some conditions for like this. You got to have x minus c is smaller than delta, right? And for this one, we have to go with n larger than n, right? Oh, actually, say so. I'm sorry. That should be there exists some natural name n, right? Such that when n is larger than n, we can take the difference of fnx and fnc, right? But you know what I mean, so that's fine. And then let's see what happens with fx minus fc. Then I said before we are going to use the classic triangle inequality. That is to say, we have to have some A plus B plus blah, blah, blah. Might be just A plus B or A plus B plus C, right? So the difference, the absolute value of fx minus fc would be smaller or equal to the sum of these n summons, right? So here we have only 3 summons. That is fx minus fnx plus fnx minus fnc. I'm gonna just write fnx minus fnc plus fnc minus fc. So you can actually say, if I wrote it into one absolute value, then this one cancels, and this one cancels. You will get directly to fx minus fc, right? But now we are going to use the conditions that we have. That is, okay, fx minus fnx. What are we gonna use? Fx minus fnx from the fx minus fnx from the continuity. I'm sorry, it's not continuity. It's from the convergence of the sequence of functions is smaller than epsilon, and so that this term is smaller than epsilon. But this one, fnx minus fnc, is smaller than epsilon because of continuity, right? So it's so the inequality is smaller than 3 epsilon, but we want to make it nicer. So we do quite simple thing is to get it to 1/3 of epsilon, and then we will get 1 epsilon. So here it's 1/3 of epsilon, 1/3 epsilon, sorry. So then we are done. We prove that fx minus the absolute value of fx and fc, the absolute value of the difference of fx and fc is smaller than epsilon. Then f is continuous at the point c, and since c, we take an arbitrary point c, so f is actually continuous everywhere it's defined, right? Okay, so this is the continuity of the uniform convergence sequence. The second one is about the integrability, right? So we basically want to talk about continuity, integrability, and differentiability. But differentiability, I'm probably gonna put it in the next video. So the second theorem, integrability, still is quite similar to continuity. If you want to remember it, just remember one of them, but just substitute the continuity with integrability, then you're done. So the theorem says, given the sequence of functions fn, if all functions in that sequence fn are integrable, and fn is converging uniformly to the limit function f, then the limit function f is integrable, right? You can actually say the integrability and continuity are of same form. So another thing is, if you are asked to calculate the integral of some sequence of functions from a to b, like this, when n approaches infinity, when n goes to infinity, then you can actually swap the limit size as the limit function and the integral function. So you swap these two actions. You first take the limit of the functions, take the limit of the sequence of functions, you get one function f. And then you take the integral of that function f, you get the answer. So we're gonna prove the theorem proof. The proof is I'm not giving you the rigorous proof or how to rigorously write down the proof, but just some ideas. So the proof would be, let's first take epsilon n. The epsilon has nothing to do with. Oh, actually, you can just take it as the just take epsilon b to be the difference, the difference of the function, the sequence of function f and nf. And actually, it's pretty much similar like how we define the uniform. Sorry, not continuity. How we define the uniform convergence. So let epsilon n to be the supremum of fnx minus fx. It doesn't matter what x is because we are taking the supremum and x is from a to b. So here all functions from a to b to r. Right? This is the assumption I forgot to say. I forgot to mention that. Okay, so you say fn is uniformly converge to f, right? So we actually know that the epsilon n is going to 0, right? So what we're gonna get? So that is to say f is actually bounded by fn plus epsilon n and fn minus epsilon n, right? This one is going to 0. So fnx minus fx is actually bounded by or we can state it in this way. Sorry. Fx minus fnx. It doesn't matter fnx minus fx or fx minus fnx, right? Because we are taking the absolute value. So, right? Then you take out fnx, then you get the inequality. Okay. And the next thing what we're gonna do is to take the upper sum and the lower sum of the left side and the right hand side respectively. So if you don't know what is upper sum and lower sum, you might go to read something about the definition of the integrability. I think I haven't uploaded anything about integrability or differentiability, but I just go right through down to the uniform convergence. So maybe later I will upload something about integrability and differentiability, but for now I just assume you guys already know what is the upper sum and what is the lower sum. So we take the lower sum of the left hand side integrability from a to b, then we get a inequality like this. Well, although I'm writing the notation is pretty much like the integral notation, but I'm not saying that I have already know f is integrable, right? I'm going to prove that f is integrable. So the notation like this and the only means the lower sum and the upper sum. I'm not saying that f is already integrable, or otherwise why we like waste time to do this, right? Okay. And another thing is, well, this, if you are familiar with the upper sum and lower sum, this is the consequence of or a property of upper sum and lower sum. No matter if it's integrable or not, you will always get the lower sum of f is smaller than the upper sum of f, right? And another thing is, actually, you can have the integral of fn minus epsilon from a to b from this side, and this side is equal to integral of fn minus epsilon from a to b. This is because we know that fn are integrable, right? This is in the condition fn, all functions of fn are integrable, and epsilon is absolutely integrable, right? It's actually like a sequence of numbers. So, well, since fn minus epsilon is integrable, then its upper sum is equal to the integrand of it. The integral of fn minus epsilon from this side is the same, right? So we have two equal signs here, two equality here. And another thing is, well, here we have this one, and these two smaller. So here we're gonna use a quite straight. I think it's a straightforward inequality. So I don't know if you guys can see. Actually, if we take like this is a b, sorry, it's a b c d, then d minus a must be larger than c minus b. Can you guys see it? I'm sorry. I checked the wrong a and d. So this should be a, and this should be d. But the equality is the same. The inequality is the same. D minus a is larger than c minus b, right? Because if you take like this, the distance between b and c is definitely smaller than distance between a and b, right? So all we have is integral of the lower sum of f minus the upper sum. Oh, actually the same if we take the absolute value. But here I'm gonna just say if we take the upper sum of f minus the lower sum of f, then it must be smaller than the integral from a to b of the function fn minus epsilon minus fn oops, this should be plus epsilon, and this is equal to the integral from a to b fn minus epsilon minus fn minus epsilon, right? Sorry, that should be plus and this one should be minus.